My name is Edward Anderson, and I'm a professor at the University of Texas at Austin. This presentation is a primer on statistics to describe random variables for those who have not had basic statistics or for those whose experience is a bit rusty. Everything in nature or life fluctuates. The temperature today is not the same as tomorrow. The shoe sizes of different people vary. The time it takes at the doctor is different every time. All of these things not only fluctuate, but they are hard to predict ahead of time. In other words, they're random. Any value that describes these random fluctuations, such as the temperature in Belize, is called a random variable. Statistics is how we describe random variables and predict, to the extent we can, how they will behave. Specifically, in this video, we will cover the three types of averages and how to calculate them. What the standard deviation is and how to calculate that. How you find the statistics of random variables that are added together. And finally, what we're going to do is zero in on behavior of random variables with the aid of the normal distribution, which is roughly speaking a description of the pattern of how random variables behave under certain conditions. While there are other distributions, the normal distribution is arguably the one most commonly used in statistics as well as the most useful. Let's begin with averages. An average describes in some way what a typical value of a random variable is. For your information, in the language of statistics, an average is often referred to as a measure of centrality. In any case, though many people don't realize it, there are many ways to describe mathematically what is typical. So there are many types of averages. There isn't just one. The most common ones that you will run into are the mean, the median, and the mode. Let's go through them one at a time. The mean, also known as the expected value, may be the most commonly used average. In fact, some software packages actually call the mean the quote-unquote average. Although that terminology is highly misleading because, as we said earlier, there is more than one type of average. The table here describes 7 observations of glucose level readings for a diabetic during the day. The readings are measured in units, and those readings, the level, is a measure of how much sugar there is in the bloodstream. For diabetics, this is a crucial thing to manage because if their sugar is too high or fluctuates wildly over the long run, it can lead to complications for their health. To find the mean, we just add up all the values that are in this table, and then we divide them by the total number of those values. To actually calculate the mean, what we do is that we're going to add up all the observations starting with 205 and then 185, and then I'm using the dots here to represent that we're going to add 154, 154, 147, 161, and then finally 188. We divide this by the number of observations, which is 7, and we're going to get the mean value for this data set, which is going to be 100 and 70.6. What that means is that the average glucose level in this data set is approximately 171. Now let's look at the more formal formula for the mean. And if X is our data set, what we're going to do is look at all the observations. The first observation will be X1, plus the second observation, which is X2. And we keep adding in all the other observations, again represented by the 3 dots, until we get the final observation, Xn, where n represents the number of observations in the data set. We then divide it by the number of observations, and we have the mean. And with this, we can find the mean for any number of observations for any data set. The median is a different measure of the typical value of a random variable. This is often used as well. For example, when you read a new article that says something like the average U.S. household income in 2017 is $60,000 per year, the average in this case is actually the median. The median is literally the middle value in a number of observations. So the median household income of $60,000 per year is that of the middle household in the country. Half the households have a higher income, half have lower. Let's practice calculating the median with our glucose readings. First, we put our observations in order from least to greatest. And here they are, sorted, running from the lowest at 147 to the highest at 205, all in order. So at this point, if we want to figure out what the median is, we just look for the middle value. And the value that is halfway between observation 1 and observation 7 would be observation 4, and hence the median is 161. So half the readings are above 161 in terms of order, and then half the readings are below 161. To give a little more context, there are situations in which the median is a more typical measure than is the mean. Let's go back to the article that said the median income in the U.S. is $50,000. In contrast, the mean of household income is quite a bit higher. It's around $75,000, in fact, and that's due to Bill Gates, Jeff Bezos, and other outliers. And so for some purposes, the mean may be misleading. And instead, the median is a more useful average to use in terms of determining what the typical household's income is. Now, there is a wrinkle on this. What happens if we have an even number of observations? In that case, what we're going to do is we're actually going to have 8 observations, which means, wow, we've got 2 middles, number 4 and number 5. So what do we do in this case? The convention is we find what is the midpoint between 161 and 185. In this case, the median would be equal to 161 plus 185. Those are the 2 middle values. We divide them by 2, and we're going to get 173. That's our median value. And you'll note that is not 170.6, so it is different from the mean. A final measure of typicalness is the mode. A mode is the most common value in a data set. In this case, it would be the most common reading. Note that we are back to 7 readings now in our sorted glucose levels. If we go down the list, we'll note that 147 occurs once, 154 occurs twice, 161 once, 185 once, 188 once, and 205 once. That means the mode is equal to 154. Let's compare the different types of averages for our data set. The mean is 170.6. The median is 161. The mode is 154. These measures are all averages, but they are all different. Each of them is more appropriate in different contexts when discussing statistics. We now are going to move to the standard deviation. First, we'll give you some intuition as to what it is and why it matters, and then we'll learn how to calculate it. Let's go back to our glucose readings. The mean here is 170.6, just as it was before. That said, it's important to understand how the glucose readings vary over the day. With diabetes, the greater the fluctuations, the more likely that eventually health complications will set in. But how do we measure these distances and the consistency? One way that seems reasonable is to just calculate the distance of each observation from the mean. The fact that the distance, 23.57, is negative indicates that 147 is below the mean rather than above the mean. Now let's compare the individual's data, which we'll call Hannah's, to that of Sally's on the other side. This is Hannah, and this is Sally. And this is Hannah's data set, and this is Sally's data set. They have exactly the same mean, 170.57. But are their data sets really that similar? Of course not, because the size of fluctuations from the mean for Sally are much greater than that for Hannah. For example, Hannah's glucose readings range from minus 23.57 to 34.43 units from the mean, while Sally's range is minus 130.57 to 134.43. The spread of readings for Sally is not good news for her over the long run because she is much more likely to have health complications related to diabetes than will Hannah. So how do we measure the spread of readings in a meaningful way? One intuitive way is to add up all the distances. Let's turn back to Hannah and do it. So we take minus 23.57 right there. The minus indicates that the level 147 is 23.57 units below the mean. We add in negative 16.57, which is the next reading. And then we add in minus 16.57, minus 9.57, 14.43, 17.43, which we represent by the 3 dots. And then we add in 34.43, which is the last reading. Divide that by 7 to get our average, and the result is a big fat 0. Well, this is obviously of no help to us. Let's try something else. Another thing we could do is to square the distances from the mean. This square is called the variance. If we notice, 23.57 squared is equal to 555.54. And we do this for all the numbers throughout the table. 17.43 squared, for instance, is 303.80, and so on. Why we do this is not immediately obvious, but hang on for a minute. If we take the square root of each of those variances, we end up with the square root of the variance. So, minus 23.57 squared is 555.54. Square root of that is 23.57. And similarly, we can go down the line. Negative 16.57 squared is 274.56. And the square root of that is 16.57. Essentially, these numbers, like 16.57, are the positive value of minus 16.57. And the reason we do that is all of these numbers are greater than 0, so we necessarily have to get a sum that is above 0. For various reasons, including one we'll get to later in the video when we talk about normal distributions, we'll work with the variances to get a single number to describe how far away the typical reading is from the mean. Doing this will capture the magnitude of the variation for the data set, or how spread out it is. Note that I said typical. Hence, intuitively, it seems we might use an average. Let's use the mean of the variances of each data point to get the variance of the entire data set. So first we add all the variances together, and then we divide them by the number of observations. So the variance of the data set is where x represents the random number in the data set, i.e. minus 23.57, minus 16.57, and so on. It is equal to 555.54, which is the variance here, plus 274.56, and then we go on down the line until we get to 1185.42. Then we divide the entire sum by 7, which is the number of observations. And the result is 413.38. And that is the variance of x. The problem, however, is that 413.38 units squared just doesn't mean much. We can't really use it to make sense of the observations, which are in units. To fix this, we take the square root of the overall dataset's variance. This gives us what is called the standard deviation. So in this case, standard deviation is equal to square root of the variance of x, which is equal to square root of 413.38. And that means the standard deviation is going to be, for this data set, 23.33. And so that means the standard deviation for this data set is going to be equal to 20.33. And what that means is that the metric of the average spread of the distance of the various readings, 147, 154, and so on, is 20.33 units from the mean. The variance of x, and x is the random variable that shows up in the number of observations that we have in our data set. Any data set, doesn't have to be our glucose readings. That is going to be the distance from the mean of each one of the observations. And so what we're going to do is take the mean observation, which we're going to write down as x bar, which is conventional, and then subtract that from our first observation, notated as x1. We square that distance, and then we add in the second observation, and the difference between that and, again, the mean of all the observations, square it, and so on. And then we do the third, fourth, fifth, sixth, whatever number we need until we get to the last observation, which is xn. We subtract the mean observation from xn and we square it. Now, we call it xn because n is the total number of observations, just like we did in the mean. And then we divide it by n, which is the number of observations. And then to find the standard deviation of x, we just take the square root of that. Note that there's a tiny wrinkle here. It says population up here. What that means is we're looking at the standard deviation and variance of just a particular data set of numbers. So for instance, we're just looking at the standard deviation and variance of the 7 observations in our glucose readings example. We'll get back to why this is important in just a bit. Let's look at Hannah and Sally. They have the same means if we look at the two data sets, but we know that they're different because the range for Hannah is -23.57 to 34.43, And that's just nothing compared to Sally, which is running from minus 130.57 to 134.43 distance from the mean. And you'll note that the standard deviation for Hannah is much less than that for Sally. In fact, you can think of the standard deviation as how distant the average reading is from the dataset's mean. If that's tough to visualize, however, just remember that the greater the standard deviation, the greater the fluctuations of the observations. Before we move to the next section, there is that little wrinkle I referred to earlier, and that is how we calculate the variance in standard deviations. So, if we are using our entire data set, such as the 7 glucose readings in our example, to calculate the variance of all the glucose readings as a whole, such as all the glucose readings over a year, we need to adjust the formula for the variance slightly. We do that by using n minus 1 for the divisor instead of n. This is referred to as the sample variance after you make that adjustment with n minus 1. In contrast, the standard deviation formula isn't different. It's still the square root of the variance, but the variance has been adjusted by this n minus 1 factor. Because of that adjustment, both the variance and standard deviation are referred to as sample variance and sample standard deviation. In practice, for my part, I try to take enough observations so that I really don't have to worry about this n minus 1 issue. Now let's move on to adding random variables. Sometimes we are going to need to add 2 or more random variables to each other. For example, the time it takes me to get into work is the sum of how long it takes for me to drive from my garage to work, which is a random variable, plus how long it takes me to walk in to my office from where I parked, which is another random variable. What would the statistics of this sum be? So let's start with an example. We're going to let x be the amount of time it takes me to drive in to work and park on any given day. And then y is going to be the amount of time it takes me to walk from where I parked to actually set foot into my office. The mean of driving into work is 20. Standard deviation is 12. The mean of walking in from where I park to my office is 30. And the standard deviation is 18. Now to find the mean of x plus y, we add the mean of x plus the mean of y. It really is that straightforward. So, the mean to drive in was 20. The mean to walk in from parking was 30. So my total time into the office on average is going to be 50. Now the standard deviation is not that simple. It is most assuredly not equal to, and I can't say this strongly enough, it's not equal to the standard deviation of x plus the standard deviation of y. That is just wrong, wrong, wrong. If you did make this an accurate estimate of the standard deviation, it would be way too high. And the reason for that is it's unlikely that I'm going to have both a bad drive in and a bad walk from where I park into my office. In reverse, it's unlikely that I'll have a really good, fast day driving in and a really fast walk in from where I park to my office. So that's the intuition behind why you can't add standard deviations. Well, if adding standard deviations is not going to work for us, how do we get that standard deviation of the sum of x and y? Well, what we can do is just add the variances. So we had the variance of x plus the variance of y. And that's going to be equal to 12 squared plus 18 squared, which equals 468. So that's our variance. And that's the correct way to get the correct variance of the distribution. To get the standard deviation, then, what we do is we take the square root of the variance in the normal manner, and the square root of 468 is equal to 21.63, and that's going to be the standard deviation, which measures the spread of driving and my walking time. So to recap, in our example, the mean of x plus y was 50, so that's my average time to get into work. The variance was 468, and the standard deviation is 21.63. The big thing to remember here is if you do the variance first, you do the standard deviation second, you will be in good shape. Now here are the formal equations for adding random variables. The mean of the random variables x plus y plus z plus how many other random variables you want to add is equal to the mean of x plus the mean of y plus the mean of z, and so on. The variance of x plus y plus z plus whatever you would like to add is the variance of x plus the variance of y plus the variance of z, and so on. And then the standard deviation of the sum of all those random variables is just the square root of the variance. The means and the standard deviations of random variables are useful in and of themselves, but in this section we'll show you how you can get even more out of them. Let's look at the average glucose readings for 100 days and plot them out. The n equals 100 in the title indicates that we have 100 observations. This plot is called a histogram. To read this, look at the bar here above the number 120. This bar represents the number of observations between 110 and 120. Reading the bar against the y-axis, the frequency, it has 22 observations. This means there are 22 observations that have values between 110 and 120. We do the same for the bar above 90, which shows that the number or frequency of observations between 80 and 90 is only 7. Let's increase the number of observations from 100 to 1,000. If we go up to 1,000 observations, we get this plot. Reading the plot works just the same. Looking at the bar above 110, for example, we see that there are 155 observations of glucose readings between 100 and 110. Importantly, as we increase the number of observations, the plot begins to have a more definite shape. In fact, if we draw a curve on top of the histogram bars, like so, the purple line is the famous bell curve. When discussing statistics, the bell curve is more commonly called the normal distribution. Sometimes engineers will call it a Gaussian distribution, but normal distribution is what you'll run into most. Let's drop the bar so we can talk about the normal distribution a bit more. Normal distributions are found everywhere, from biology to demographics to economics. They show up anytime that a result, such as blood glucose in this case, is the sum of a lot of little random effects. So if you keep adding more and more independent variables like we did in the last module, eventually the sum will inevitably begin to look like a normal distribution. All sorts of random variables, an individual's blood pressure, the average men's shoe size, or the temperature on July 25th in Belize have a normal distribution. Let's standardize the purple curve by translating the measurements on the x-axis into how many standard deviations there are above or below the mean. On this curve, the mean of the blood glucose readings is 120 units, and the standard deviation is 20 units. And so, if we look at 120, it will be exactly 0 standard deviations above the mean, obviously. Then, if we look at 140, which is 1 standard deviation above the mean because it's 20 more, we've got 1 standard deviation above, and then add 20 more, we're at 160, so we're 2 standard deviations above and so forth. Similarly, if we take 120, subtract 1 standard deviation, we're at 100, which is 1 standard deviation below the mean, or -1. So let's take these numbers here, move them down to the x-axis, and see what we get. What we get is what is called the standard normal distribution. And what that means is every value that was in that prior graph, or any other histogram with any other sorts of measurements, is mapped into how many standard deviations it is above or below the mean. So in our prior example, remember 120 was the mean, so it's 0 standard deviations above the mean. 120 plus the standard deviation of 20 is 140, which is 1 standard deviation above the mean. 120 minus the standard deviation is 100 because the standard deviation again was 20, and so on. And those all propagate nicely down to here. What you want to take away from this is that 120 has what we typically call a z-value. Z-value is the number of standard deviations above or below the mean of 0. 140 would then have a z-value of 1. 100 would have a z-value of -1, and so on. The y-axis is also standardized and is called a probability density. And it's set up so that if you add all the area under curve, like you would if you're integrating in a calculus sense, all this area would add up to 100% or 1.0. This is going to help us out quite a bit later. Now, let's calculate a z-value of a number. We'll start with 150. To find the z-value of a number, you just subtract the mean from it, and divide by the standard deviation. So let's do this. The z-value of 150 equals 150 minus the mean of our glucose distribution, which is 120, divided by the standard deviation, which is 20, which gives us a z-value of 1.5 for 150. In other words, 150 would lie right here. Now, why all the fuss? If we look at any normal distribution, there are regular patterns of probability. For example, the likelihood of an observation having a z-value of -1 or less than -1 is 15.9%. So any observation has approximately a 16% chance of being at least one standard deviation below the mean. If you're a calculus fan, this would be area under the curve from here to here. Of course, strictly speaking, it would be from -infinity to here, but -4 and below, the normal distribution is essentially 0. So let's do the same for the likelihood of an observation having a z-value of less than 0. Remember, this is the mean. It's going to be 50%. So if we draw up all this area, that's going to be half the standard normal distribution, and hence the odds of a reading in glucose terms of being under a z-score of 0, remember that's 120, which is the mean, is going to be 50%. Let's flip this on its head. Let's say we want to know the 90th percentile of this distribution of glucose readings, which means if we take a reading that it will have a 90% chance of being equal to or less than this value. Looking at a chart of z-values, the 90th percentile always translates into a z-value of 1.28. And that corresponds to the 90th percentile. Which means if we figure out what all of this area under this curve is and add it up to z-value of 1.28, that's going to be 90%. So let's figure out what the glucose reading specifically would be. So if we want to know what the 90th percentile is, all we have to do is add the mean of this distribution plus 1.28 times the standard deviation which equals 120 plus 1.28 times 20, which equals 145.6. In other words, if we take a reading, there's a 90% chance that's going to be 145.6 units or less. Again, this idea would work for blood pressure, shoe size, temperatures in a tropical paradise, and so on. The 90th percentile of any of these distributions will be 1.45 0.28 standard deviations above the mean. One little last point. The center of this distribution is clearly here at 0. Remember, 0 is also where the mean is. Finally, the mode is where the most frequent observation, or highest probability density in this graph, is. Looking at this curve, the highest point also has a z-value of 0. In addition, if we look at this, 50% of the area under this curve, in other words, 50% of the probability distribution, is going to be below 0. And if we look at the other half, that's going to be 50% as well. So 0 is the value where 50% of the distribution is less, 50% of the distribution is above. So you have a 50% chance of being below and a 50% chance of being above. That means 0 is the median. So in this case, for the normal distribution, the mean, the median, and the mode are all 0. This won't generally be the case, but for normal distributions, it is true. That's going to help us quite a bit. Now, to recap, we have learned about averages. We have learned about standard deviations. We have learned about adding random variables. And we have learned how to use the normal distribution. With that, I thank you.